Alrighty, folks. So, metamorphic rocks. Metamorphic rocks. You've probably picked up on the fact that I don't really care that much about metamorphic rocks at this point this semester. It's not. They're actually some of the prettiest rocks out there. They really are. Some of the nicest are absolutely beautiful. Marble, of course, absolutely beautiful stuff. It's just, I don't know, never caught my fancy as far as studying it. It's fairly straightforward. I'm sure if I managed to go a little deeper, I'd uncover all kinds of wonderful mysteries. But yeah, and again, at a 100 level, gosh golly, there's so many other chapters in that book that I don't want to say are more important, but that are better time spent on. All right, so as such, we really don't get to talk about metamorphics that much. You guys have a working knowledge already. You can tell me what that rock is right there. What is that? It's striped, so it's a banded stripe, the zebra stripe rock. Nice. Yes, it's a very nice rock. Yeah, that's a nice, all right. And that's pretty much true, unless you're looking at a hunk of sandstone, and you'll be pretty darn sure when you're looking at sandstone, because it looks like sandstone. If you see a striped rock out there, it's going to be nice. And, you know marble came from limestone. You know that good coal, anthracite, comes from yucky coal bituminous. And you know slate used to be mudstone. That's enough to get you out into the world. And we're done. No, we're not done. But, let's see. Remind you some stuff you already did, in fact, know. So, metamorphism, what is it? Mineralogical or textural changes that occur in a rock due to exposure to extreme pressures and or temperatures. And every time I read that, I think my and or is in the wrong place. You're always going to get the temperature change. You don't always get the effects from the pressure, though. Okay? So my and or is in the right place. And I've trained Siri so well, I was texting my daughter about and or, the show, the other day, and it actually wrote the and sign / or. Good Siri. For once. So exposure to high temperatures, and sometimes high temperatures and pressures. So, we see that. Well, gosh, where do we get this warmness from? The center of the Earth is really, really hot. All right? Really hot. In fact, it's so hot that it melts rocks. It melts metal. I don't know what you think would be harder to melt, metal or rocks. Depends on the metal, I guess. But we hardly ever melt rocks, right? We put them around our fire pit. You could throw an aluminum can in and sort of melt that. But not the rocks. Well, luckily, thanks to the geothermal gradient, it's not that hot all the way through. We know at the surface of the Earth it's quite nice. But as you go in, once you get past cave level where it's always cool, the Earth does in fact start to heat up. Approximately 1 degree Fahrenheit for every 70 feet that you go in. And I haven't done the math recently, but if you multiply that by the radius, hopefully you end up somewhere around 9,000 degrees. I have a feeling it's not a very linear curve, though. I'm guessing it gets pretty logarithmic at some point and just keeps jacking right up. But as far as most folks are concerned, though, that definition of geothermal gradient does work. So we have to get these rocks fairly deep down is the idea here. All right? Exception, I forget, hot spots. Every so often the hot comes to the rocks, right? We talked about hot spots forming the Hawaiian Islands. That was a volcanism example. But it doesn't always break through, all right? The magma, the hot spot, bless you, doesn't always break through. And it is certainly going to have an effect on the rocks around it. We had that renegade question, at least on the on-campus test, about bake zone. All right, you're going to hear that officially today. But the rock around that intrusion is certainly affected by that high heat. Well, how do you get burial, or how do you get pressure then? Pressure, we list burial here. That's not enough to make huge changes. We still think of burial as a compactionary force at this point. Lithostatic is a big, scary looking word. Lith, we've mentioned it a couple times. That just refers to rock, all right? And static, I don't know if you guys have ever tuned in a radio with a knob before, but there used to be something on a TV called static in between the channels. Static actually comes from the word stasis, which means constant or steady. And boy, static is anything but that, but that's what it means. So constant rock pressure. In other words, again, that's just the weight of all the rocks above you squeezing down. And we talked about that with sedimentary rocks a little bit. We rely on that to get rid of our pore space, make stuff easier to glue together. So the idea that that same pressure can cause some mineralogical changes, some textural changes, I should say. Well, you got to have a lot. You got to be buried really, really, really deep. Okay. And again, not that can't happen, but typically when we talk about metamorphism from pressure, we're talking about big changes. Those giant swirls in your gneiss and the handful of your other rocks, the schist, the big crystals all lining up like fish scales. Okay, that kind of stuff that comes from like plate tectonics. That's continents bashing into one another kind of pressure. That's mountains going up. You're going to find metamorphic rocks, even if you're not going to find a lot at the surface here, but if you go into mountain ranges, even up into the Adirondacks here, okay, in the core of these mountains, there's metamorphic rocks. So when we talk about pressure, think big scale, big scale. So here's an example of lithostatic. It's constant, it squeezes. And like I said, I may have underplayed it a couple minutes ago, but that's not typically what folks think about. Because this isn't even going to give you those slight ripples that you see in the phyllite. Remember, when we move from slate to wavy slate, you start to see those little waves in there. That too is directional. That's coming from your mountain building events. So differential. Here's the side to side. Okay. This is what gives us our orientation. This is what allows us to move mineral grains around. I'm not going to quiz you on the different types of stress. We're just reminding you that they exist. So again, changes that can happen during metamorphism. If you don't know it, the triangle there, delta, is sort of the shorthand for change in science. All right, so change in temperature, change in pressure. Capital T is temperature. Lowercase t, by the way, is usually time. And capital P is pressure. And we're stealing some nomenclature from chemistry and physics here, but you don't need to worry about that. So mineralogical changes primarily come from texture and from temperature, and this is where we talked about the grains of silt and clay, the mud finally growing and growing together and becoming rock. That's slate. The sandstone moving to quartzite, those grains of sand melding together and becoming. And I know you're thinking that, well, isn't that also sort of changing the texture? Yeah, you're right. But they don't call it that. Acknowledge that, you are going to see some difference from sandstone to quartz. It's going to become, in that case, probably a much rougher, coarser grain. But usually for textural changes, they're looking at the much more larger scale reorganization of the grains, the reordering of the grains, that banding that we see. So. Now, I didn't mention this. You can, in extreme situations, get a recombination happening. It just came up in the book, and I don't know that you guys are going to read the Metamorphic chapter. You certainly, if you have the time, you should. Whenever I talk to you about it, we mentioned this first one, okay? And I always give you the example of kind of putting the cookie back in the oven until it grows just a little bit more until it's just right. This increase in grain size, it melds your grains together, your crystals together. But in some circumstances, you could get a remixing and a remaking, which is kind of neat. And that might even account for some of the color changes and whatnot that we see in there. Some of the impurities are mixing in and recombining. So again, moving from, I was going to say, I'm not sure if this is sandstone and a quartzite, but let's use it that way, but I see the fine print right there. So your grains of sand, there's plenty of pore space in sandstone. It's an aquifer, it can hold water, where water runs through sand all the time. But by the time you throw that back into this metamorphic oven, those crystal grains have grown together. They've grown bigger and grown together. Your pore space is gone. You hardly ever talk about an aquifer with regard to metamorphic rocks. And again, an aquifer would be a body of rock that we get water out of. All right, so reflecting back to lab here, again, textural changes, okay? For textural changes, we're looking at that word foliation. I just want to remind you that the foliation can be anything from just those subtle little ripples in your phyllite to the complete reorganizational structure of the gneiss and everything in between. Think of the fish scales of your schist, okay? And that, as I indicated a few slides back, quite frequently is your differential stress, the angular force, not the compaction. So again, a wonderful example of foliation there from our cover slide. Not just the banding, the layering itself, but the fact that it is also kind of swirling around in some cases. Metamorphic grade. They talk about low grade, high grade, and it really is just a measure of how long it's been in that metamorphic oven. how long it's been exposed to high temperatures, how much pressure it's been exposed to. A little bit, you get your slates, and your slate may be starting to turn into a bit of phyllite. All the way through to, holy cow, those crystals are popping out, and they're lining up like fish scales or sequins. Then also on here we've got the idea, and I think I mentioned this in lab to you, that these are also sort of adjectives. Okay, slaty, schisty, gneissic. Okay, they use these as descriptor words. Obviously, something that is gneissic is going to display the properties of a gneiss. Something that is schisty, okay, is going to have that shiny, shiny schist. Remember, always shiny schist. And then you also see that straight line comment on there, and that again is the way we learned it in lab. All right. For those of you that may be listening to this in Earth Science class, you didn't do, Metamorphic's rock lab per se, but we basically started with a piece of mudstone, a sedimentary rock, went on to slate. Slate grew into phyllite. Phyllite grew into schist. Schist grew into gneiss. All right, and we said that is something you can do in nature. It does happen in nature, but I don't know that there's an end on here. Well, the rocks are here at any rate, for example, while I'm talking. But also the fact that, and you guys on campus here know, geology students on campus or online, know that the higher end stuff, schist and gneiss, you can actually start with any rock. Okay, turn anything into schist. So, but we also learned it as a straight line metamorphism. So again, low grade on the low end here, all the way up to high grade over here. And if you need to picture that in your mind as simply a function of depth, that's not a bad idea. Okay? It's not a bad idea. That certainly will increase the temperature at least. Temperature or pressure is definitely a little more situational, but picture is depth. Now, how does it get into there? Well, again, that's a function of plate tectonics. We don't generally have a crack form at the surface of the earth and this rock falls through to the gates of hell or something like that. It's brought through in a very long sort of conveyor belt process, okay, of plate tectonics. So yeah, it's I don't want to say it's rare because there's certainly tons and tons of rock down underneath there, but the idea of a rock from the surface getting brought down in is rather complicated. It's a long process. Then the big fancy word protolith, where I'm trying really hard to stop using parent rock. All right. Proto means early. Prototype, heard of that. Protozoa, early life. Proto means earlier first. Lith again is rock. So what is the first rock? Well, that also kind of serves as a parent rock. If you think about slate as a daughter rock, okay, the parent rock was mudstone or shale. So the rock it was before it became metamorphosed. I love to freely conjugate, pardon me sometimes. So before it was exposed to metamorphic conditions. And you know all your protoliths. I know you guys do. We just ran through a handful of them a little while ago. What's the protolith for marble? Nice. What did I hear? Protolith for marble. What was marble before it was marble? What? Yeah. Limestone. I think I heard a limestone out there. We just reviewed these 15 minutes ago. Slate. Slate was, yeah, mudstone or shale. Excellent. Quartzite was. Sandstone. So quartzite, quartz. Remember quartz? Quartz is crystally, sandy stuff. Lime, calcite. Limestone's calcite. So you're not going to make a quartzite out of a limeade there. Anthracite coal. Give me one more chance. Bituminous coal. Good. All right. So again, not that there's going to be a huge parent rock matching section on the test, but it wouldn't hurt to brush up on those. Okay. And for those of you that took the rock test, again, just not earth science folk, you know, that was your third column choice for Metamorphics, was what it was beforehand. For foliated rocks, I don't usually focus on that too much. It's always the rock beforehand. So in that metamorphic grade we just showed you, where shale makes slate, slate makes phyllite, phyllite makes schist, and schist makes gneiss. Schist is the parent rock for gneiss. Phylite's the parent rock for schist. Slate's the parent rock for phyllite. And shale's the parent rock for slate. It's always a step before it. And there's what we just said again. So it works backwards. This came from that came from this came from that. And we didn't even mention the word blue schist to you guys. There it is. So I did make a quiz at some point. So I would be prepared, again, just conversationally. You know, I find myself at 53 points on the test, and I got to come up with 2 more questions real quick. I'm going to throw something stupid like this on, okay? Because I like to have nice, even numbers on my even points on my test. Because there's really not a whole lot. In all honesty, let me make sure there's not a whole lot more slides here. Yeah, there's only one more slide. In all honesty, there's not a whole lot of this that's going to be test-worthy material. All right, I'm obliged to talk to you about metamorphic rocks, as I indicated. I'm not obliged to test you on them. So I want you to remember the basics. Metamorphic rocks are rocks that are affected by exposure to high temperatures and pressures. High temperatures makes you non-foliated. Temperatures and pressures makes you foliated. Parent rocks, and that's really about it, okay? So, other than the connection to igneous intrusions, okay? You're in a position, at least this semester, where igneous intrusions and this material aren't on the same test, and that's how that crossover question about bake zone happened. But you may see some repeat questions about this. I think one of my favorite, and I forget how I worded exactly, but if some magma intrudes into a layer of limestone, what type of rock would be formed in the bake zone around it? Now you guys just learned that limestone is the parent rock for marble. Good. Okay. So if some magma intrudes into marble, into limestone, it could make marble in that bake zone. So if you were, again, imagine that road cut, you're driving down the highway, you would see a big old, probably dark black igneous intrusion there, a dike in the rock, and then around that you'd see some marble, and then if you went farther out, you'd see limestone. Bake zone really is the equivalent of a bonfire, okay? The closer you are to that bonfire, the hotter it is. So that bake zone happens right at the intrusion, and as you get farther away from the intrusion, it fades out. And this is called contact metamorphism, as the title implies. Okay, this is not bringing a rock down in and heating it up and squeezing it. This is bringing the hot stuff to the rock. Hardly any pressure. Yeah, that magma squeezing through that crack and expanding. It's going to, sure, it's a tight fit, but that's not, again, the kind of pressure that changes rocks. This is all temperature stuff. So there's no rocks on here, no rock types implied here. Okay, but around any one of those given intrusions, you're looking at potential bake zones. Salud. Questions? Comments, concerns? All right. So I do want you to read the weathering and erosion chapter, okay? When you guys get a chance, we're going to talk about it next time we come back. Again, it's a lot of vocab. So the more you're familiar with those words and hearing them for a second time instead of just the first time, the easier your note-taking will go.